All right. So yeah, the first quizzes, the scores were pretty good about what I would, about where I would hope they would be. But you know, if you didn't get the average wasn't 100. If you didn't get 100 on it, I mean, to me, that's just, you can get those points. You just need to understand the homework. And so if you don't understand something in the assignment, let me know, and we can figure it out, and then you get those points. Okay. Does anyone have any questions about, how about first well, let's talk about the quiz when I hand it back. So sorry I didn't bring that back today. Anyone have any questions about the assignment from Friday? Yep.
Well, on number 4, we have the three-dimensional matrices, and you're asking about find the force vector that the cable applies to the beam.
Oh, yeah?
In the 2D, you find the angles, right, for X, Y, Z?
You could do that, but it's easier to just do it like, do you happen to have the problems with you?
I do.
Well, maybe, could you read out? Okay, so this is in the, this is from the Friday assignment, right? And it's the one where you have a beam like this, right? And a cable connected to another wall over here, and it gives you the, yeah. So in 2D, what were the points that it gave you?
Point A was 1, 1, and point B was 4, 2.
Okay, so first, A is 1, A is 1, 1, and B is 4, 2. Okay, so in 2D, you could figure out those angles, but there's an easier way even in 2D, and it's the way that works a million times easier in 3D, is to say, if you look at part of the free body diagram, this is the direction of the force we want. And so we want it pointing towards B from A. So you can go figure out a vector that's pointing in that direction by just subtracting these two. So V is equal to B minus A. So 4, 2 minus 1, 1 is 3, 1. And so that's a vector in the direction you want. It's just not a unit vector. Well, you have to do one more. Right, but you have to do one more thing with this before you get to what you're talking about. First, you have to make it a unit vector in that direction. Right now, it has a length of 3 point something, So the magnitude of that vector is this. And so the unit vector is 3 over root 10, 1 over root 10. And so then, yeah, the force vector is just T times this unit vector. In 3D, it works just the same way. And so yeah, you can, in 2D, you're like, okay, well, it doesn't take too much more time to just calculate the angles and stuff and use sine and cosine. In 3D, that turns into a nightmare, although there is still a way you could do it. I don't think I could probably work my way through it off the top of my head. But so let's say that, can you give me those 3D points?
Okay, point A is 1, 1, -1.
Okay. Okay, so we'll do it the same way. We want it we want a unit vector going to B from A. So V is 4, 2, 1, minus 1, 1, negative 1. So 3, 1, 2. The magnitude is 3 squared plus 1 squared plus 2 squared. So what's that? 10, 14. And so the unit vector is 3 over root 14, 1 over root 14, 2 over root 14. And then the force vector is this times, is t times that unit vector. In 3D, it's hard to imagine any case where you want to work with angles because you have to do angles in about different axes. Yep.
I know in the two-dimensional problem that we did, that was question 3 technically, but now I know we're doing it assuming that it would apply to the beam, but the question is, does the force apply to the wall? So then we're just reversing the direction.
That's right, just reversing it. So when...
We have to have a free body diagram with respect to the wall.
That's right. You could think of like a free body diagram of, I don't know, a chunk of the wall or something. And then that force would be going this way, yeah. So you just have negatives where you have positives. Any other questions about the assignment? Yeah. Oh, yeah, so those were just asking you to symbolically go through the chain rule and the product rule. So 8. We want a d dx of q v, where q and v are both functions of x. So that's the product rule. So it's dq dx times v plus q times dv dx. Or since both of these are just functions of one variable, you could write that as q prime v plus q v prime. That's all I was looking for there. And then same idea with 9. Those are functions of t. So d dt of u cross v is u dot cross v plus u cross v dot. That's all. Okay.
I just didn't quite get it.
Yeah, right. I understand. Any other? Yep. Sure. Can I I'm sorry, I missed the last part.
Because I'm working on that, but I feel like hard. I can do something, but after that, I think I can solve it.
Okay. Okay. So number 6, d dt of 2xt squared. Oh, right. This is that differential. Yeah, this is a tricky one, actually. I mean, it's tricky, not like it's tricky can mean like complicated. This just means there's a trick, and then that's it. Okay, so here's the trick. So remember this one. X of 1 is equal to 5. Okay. All right. Well, the first thing you might think here is take the derivative. So you get, let's see, 2 x dot t squared plus 4 4xt is equal to 50. Okay, so that's probably the first road you would think to go down. Now we have a new form of this differential equation. The question is, can we use separation of variables to solve it? And we can't. There's no way to get all the x's on one side and all the y's, all the t's on the other side. Okay, so that's a dead end. So instead, here's the trick. Define a new variable. Think of z as being equal to, you could do it without defining the new variable, but this is just going to make it, the notation, a lot simpler. Okay. Then your differential equation is dz dt is equal to 50. Okay, so let's just work with that for now. That's easy to solve. You get integral of dz is equal to integral of 50 dt. So you get z is equal to 50t plus c. And now we'll rewrite that as, we'll plug back in for z, so 2xt squared is equal to 50t plus c. And now we can use our boundary condition. When t is equal to 1, x is equal to 5. So we have 2 times 5 times 1 squared is equal to 50 times 1 plus c. So 10 is equal to 50 plus c, or c is equal to negative 40. And so now plug that back in, and you get 2x t squared is equal to 50t minus 40. And now you could divide both sides by 2t squared and get x as a function of t. If you left it like this on a test, I'd give you full credit. It's fine with me. This is a relationship between x and t. And I always appreciate a good effort at laziness, so good for you. But what do you get here? X of t is equal to 25 over t minus 20 over t squared, something like that. So the basic idea is that you have a total derivative of some complicated thing. Define a new variable that's equal to that complicated thing, solve that, and then work from there. And actually, this is the idea. This simple idea is what's it called? The method of coefficients of integration or something. there's an approach that you learn in differential equations that's based on this idea, although it sort of uses it in reverse. The idea is actually, okay, well, the idea, so the way you have to do it then is say you're not given this, okay? This is kind of guiding your hand once you know this trick, okay? What if you're given this instead? You know? Like, it's not so, it doesn't jump right out at you, but the fact is that this two-term expression is a total derivative. And if you can recognize that, then you can use this idea. And if it's not quite this, but you can do a little manipulating to make it something like this, you can use that idea. So, any other questions on the assignment? All right. So we'll do another quiz on Friday, and it'll be based on this assignment that you got and the one that I'm putting up today. Okay. And the one I'm putting up today, I'll try to make pretty short. All right, so now we're done with all the mathematical preliminaries, and we're going on to particle kinematics. And really, particle kinematics, okay, so we're doing particle kinematics in inertial reference frames. Sorry, let me be a little more specific on that. Particle kinematics in non-rotating coordinate systems. Okay, so we'll be dealing with, so we have a coordinate system where the axes are not changing directions, and you have a particle up here, and the location of that particle is represented by a position vector p of t. And basically, we're just trying to track this p of t as the object moves around. And the key idea is just that the velocity is a function of time, is the derivative of the position vector. You can also write that as p dot. And the acceleration as a function of time is v dot or p double dot. And so if you're given these as, if you're given acceleration, position, or velocity as a function of time, you can write it as differential equations to go one direction, or derivatives to go the other direction. Okay, so going one direction is, this is the one you kind of hope for. Neither are too terrible, but you know that if you're going in the direction from position to velocity to acceleration, you don't need any information besides the functions. You don't need any additional info besides the function itself. On the other hand, if you're going so really what you're doing is you're not exactly integrating, you're using separation of variables. But if you're going in the direction from acceleration to velocity to position, you need boundary conditions, because those boundary conditions are what let you put numbers on the constants of integration. So you need a boundary condition for each step. Let's say to find the constants of integration. Okay, so as an example, let's use the constant acceleration equations. And let's just do it for motion along a line so that we don't have to worry about, multiple components. And, well, now let's do it with all the components, just so you can see it with vectors. Okay, so first, say that you're given that the x velocity, okay, so like the velocity vector is a function of time. That's Vx, Vy, and those are both functions of time. Is equal to V0x, V0y plus t times ax, ay. Okay, say you're given that. I'm making you erase a lot of stuff. Sorry about that. So first, let's figure out what the acceleration is as a function of time. These are constants, and these are constants. Okay, so to find the acceleration, we're going in the direction where all you need are derivatives. So we don't need any constants of integration. We can just differentiate. So v dot is equal to, take the derivative of, you're just taking the derivatives of x and y separately. Derivative of this constant is 0. Derivative of this constant times t is just the constant. Same thing for y. You get 0 plus ay. And so the acceleration as a function of time is just a constant vector, okay, which is, these are the constant acceleration equations. So that checks out. Okay, but going the other direction, any questions about that? You follow what I'm doing? Going the other direction, what's the position as a function of time, given that px at time equals 0 is equal to p0x, and py at time equals 0 is equal to p0y. Okay, so what we have is, I'm going to write this as a system of two differential equations. Okay. The first one says Vx is equal to V0x plus AXT. And to write that as a differential equation, we know that Vx is the derivative, the time derivative of Px. So this is Px dot is equal to V0x plus AXT. And the second equation says Vy is equal to V0y plus AYT, which is equivalent to saying Py dot is equal to V0y plus AYT. Okay, so this is our differential equation. Is it ordinary or partial? Ordinary. What is the independent variable? Right. What are the dependent variables? Px and Py. It's a system. Is it coupled or uncoupled? It's uncoupled because there's no, for it to be coupled, you'd have to see Py's in the Px equation and Px's, we don't have that. The t can appear in both of them. It's the dependent variables that can't cross over for it to be uncoupled. And then they're first order, so so it looks like we have enough boundary conditions. Okay, so for the first one, we have dpx is equal to v0x plus axt dt. Integrate both sides, and you get px is equal to v0xt plus 1/2 ax t squared plus c1. And we can use this first boundary condition that says when t is equal to 0, px is equal to this constant p0x. So we have p0x is equal to 0 plus c1. So c1 is equal to p0x. And so the final form is that px as a function of time is equal to v0xt plus 1/2 ax t squared plus p0x. Same approach for py. And you get py of t is equal to v0y times t plus 1/2 ay t squared plus p0y. And you've seen those equations before. Any questions about that? Okay, so going the derivative direction is a bit easier. Takes less time. But it's worth keeping in mind that if you're going this direction, you don't need anything new. If you're going from acceleration towards position, any one of those steps, you need to have boundary conditions. I want to talk about two. This is. Let me see if I can. I don't have one here, but let me see if I can come up with an example using the chain rule. So I brought up last class that this is a way that the chain rule is going to come up some in this class. So let's say that you have, okay, so first the idea is that if you have velocity given as a function of anything, I'll call it q. Usually it's going to be x, y, or z, like it's going to be a function of one of the position components. Then acceleration, and the idea here is that q is implicitly a function of t, but we don't know okay, so this variable q, it does depend on time, but we don't have any information about what that dependence, what form that takes. Okay, this is a way that you can calculate the acceleration. So the acceleration is equal to the time derivative of the velocity. We'd like to just be able to take that time derivative, but we can't in this case. So instead, we're going to use the fact that dv dt can be written as dv dq times dq dt where this can often be determined, can often be expressed as part of the velocity vector. Okay, so let me give an example. This example is going to be a lot clearer than that bullshit. Okay. I'll edit that out on the video. Otherwise, they'll take away my YouTube membership. Okay. So let's say that we have velocity that's equal to x squared 2x. Where x is the x component of the particle's position. And we want to calculate the acceleration. As a function of x. Okay, well, the acceleration is equal to dv dx times dx dt. Dv dx is 2x 2 dx dt is just the x component of the velocity, right? That's if x is the x component of the position, that's the definition of the x component of the velocity. So we can just replace that with this is the x component of the velocity. And so you get 2x to the third 2x squared. And that's a function defining the acceleration that we got from differentiating the velocity, even though we didn't know the dependence on time. That's pretty cool. That is useful pretty often. Any questions about that? Okay. So the mistake you definitely do not want to make is when you see problems like this is just, and this is a mistake people make all the time, so don't be the one to make this mistake. You see that this is the velocity, you see that you want the acceleration, and you just think acceleration is the derivative of velocity. And so you just take the derivative with respect to x, and that's it. That's not correct. Acceleration isn't the derivative of velocity generally. It's the derivative of velocity with respect to time. Okay? And so you can't just take that derivative with respect to x. That's this first part, but you have to deal with the chain rule part too. Okay? Okay, so now let's talk about circular motion. So this omega vector is the angular velocity vector. It represents, so let theta of t represent an angular position around a given axis. Then the x component of the angular velocity is d theta about x dt. The y component of the angular velocity is d theta y dt. And the z component of the angular velocity is d theta dz dt. Okay, you have to define it in sort of this awkward way, the angular velocity, because there's no such thing as a vector angular position. It's a nuisance. It causes a lot of difficulties in dynamics, but it's just how it is. So you can't represent an angular position as a vector.
Even spherical or cylindrical coordinate systems?
An angular position. in, I don't know. I'd have to think about that. Well, I guess I would say, so when you're talking about, yeah, even then, because what you lose when you're trying to define an angular position vector is you see that the order of, okay, so here's what, there are certain things that are required for things to be a vector. You have to be able to add them in different orders. They have to have multiplication relationships. You have to be able to change coordinate systems. And the problem with representing an angular position is the order of operations just matters with finite rotations. There's nothing you can do about it. So if you, so say this is the x-axis and this is the y-axis, you know, 90 degrees that way followed by 90 degrees this way. Where did I start here? Yeah. Is different than 90 degrees about y, doesn't move it at all, followed by, I don't know, was it different? I might have given a bad x, right?
Like x to y to z.
Okay, well,
X to z.
anyways, that's the idea of how, of why it's like an order of operations thing. Like doing your rotations about the axes in different orders gives you a vector that's pointed in a different direction.
Okay.
And that's the problem with trying to represent angular positions as vectors.
Okay.
Well, and even with things like spherical coordinates and cylindrical coordinates, that's extremely useful for trying to define a position point based on like a certain curve. But then as soon as you try and involve the motion, then it just falls apart.
So, okay, so for us right now, the bottom line is just we have sort of this awkward, I'm not defining an angular position vector because there's no such thing, but I am defining an angular velocity vector because then you're talking about infinitesimal angular changes, and that works fine as a vector. So you can add up angular velocity vectors. They meet all the properties that you need for vectors. And then the angular acceleration vector is just the time derivative of the angular velocity vector. So that's a simple relationship. The relationship with angular position and angular velocity is more complicated. But at a given instant, for a particle moving in circular motion, particle in circular motion, with angular velocity omega, angular acceleration alpha, and r, a vector r, pointing from the center of the circle to the particle, the velocity of the particle is equal to omega cross r. And the acceleration of the particle is equal to alpha cross r plus omega cross quantity omega cross r. In this class, for us, accelerations are going to be especially important because when we get to kinetics, that's how you relate forces to kinematic properties, kinematic quantities. And so this second equation is going to be important, and it's sort of complicated, so here's how I remember it. All ripe watermelons will rot. Sort of a pessimistic view of watermelons. But so you have to, this alpha is an A and this omega is a W. All ripe watermelons will rot. The watermelon equation. Okay, that's what I'm going to call it. And that's one that I think, I'm pretty sure in the list of programs for calculators, that one's in there. We'll use it all the time, so it's sort of nice to just be able to enter in these three vectors and it does that equation for you.
Will you label us the watermelon equation?
No. No, only internally. Okay, well, let's just stop there, and I'll do an example using this next time. Okay, so we'll start with class on Friday, and then do the quiz at the end.